Welcome everyone. This is our fourth meeting of our small SIGCOMM Paper Reading Group. So at today's meeting, we will start study the paper of Decentralized SD Architecture for the Wide Area Network. It's a paper published at SIGCOMM this year, and I read the paper before, so I enjoy reading it. I think the idea is quite clean and elegant. And because today we will have Chengjing Zhou from Nankai University. She's a PhD student working on programmable networks, and she will do the presentation for about 35 minutes. And after that, I will have a discussion with Chengjing and the first author of the paper from UC Berkeley, and also we will also do questions from the audience. And Alex, there are, as you can see, there are probably around 40 participants at the Zoom meeting, but because there are also about the same number or a little bit more audience from joining our meeting from Tencent meeting, because in China sometimes it's a little bit difficult for people to know. So we are essentially doing rebroadcast at the Tencent meeting. So don't worry about the audience. They are about this. So for audience, I will ask you to please mute yourself. Hello. For all the audience, please remember to do. Yeah, I see. I think the problem probably comes from my microphone, but I will give the floor to Chengjing to start the presentation. But in the meantime, I will change to a different microphone. So I'll do that. Okay, Chengjing, you can start. Thank you.
Okay, thanks for the introduction. Okay, can you hear me?
Yes, we can. Yes.
Okay, here we go. Hello everyone, I'm Chengjing Zhou from Nankai University. I'm excited to share the paper, A Decentralized SDN Architecture for the Wide Area Network, published in SIGCOMM 2024. This is a joint work of Google, UC Berkeley, and Cornell University. Now, we are all aware of the importance of the global WANs play in enabling planet-scale computing. When WAN outages occur, there is a huge impact on users. We see this situation across all major cloud providers. In Google's WAN outage statistics, we can see, despite decades of experience and plenty of practice, outages continue. While minor outages may be expected, the continued occurrence of large outages is more concerning. Outages are rarely caused by the loops, dead ends, protocol bugs that the network research community can handle today. Rather, experience shows these root causes to be diverse and complex, often cascading across components. For example, in one outage at Google, a latent bug existed in the job scheduler. A few months later, unrelated maintenance operation triggered this bug, killing SDN controller jobs for a portion of the network. Affected traffic then fall back to shortest path routing, resulting in severe congestion until the controller were restored. Notice this outage spans job scheduling, data center maintenance operation, and SDN controller jobs. From this outage, we can see that the root causes of many large-scale outages are very complex. Thus, in this work, the authors aim to tackle large outages by considering what can be done at design time to limit the occurrence of such complex outages. Now, network researchers apply some techniques to prevent outages today. The first, isolation, which is sharding or partitioning the network to limit the scope of any single failure. The second, diverse redundancy, which minimizes single points of failure in the network. And the third, formal verification, which models the network and attempts to formally guarantee the network always has correct behavior under certain expected conditions. However, these techniques do not address complex failures that span multiple components, and once continue to experience this large-scale outage. The author observed that a common root cause for these large-scale outages may be the complexity of the architectural components and the interactions between them. Therefore, in this work, the authors turn to simplification to help reduce the occurrence of outages. More concretely, what components can be taken out while maintaining functionality, performance, and the cost we have to expect or rely on. Now, let's start with some background. SDN is born of protocol-based networks, which rely on protocols like IS, BGP, and RSVP to establish connections between routers and maintain these connections when network events such as link or router failures occur. Decades of using these traditional protocols showed they were survivable, but were inefficient and difficult to manage, evolve, and scale. Therefore, over the past few years, large-scale wide area networks have shifted to SDN-based architectures with a central control program written by the network operator that read network states, compute paths, and program these paths into the network. Although the concept is very simple, the reality is much more complex. First, to handle global scale, the control program is hierarchical, with intermediate control jobs spanning the globe, providing aggregation of control operation up and down. All control jobs require running on a network operating system, also called NOS. And NOS which runs on dedicated physical hardware in data centers around the world. And they are managed by cluster management software. For these controllers to reach the routers and each other, a control plane network, also called CPN, is needed that is also spread across the globe. Collecting and providing abstract input to the controller then requires dedicated demand and topology services. Finally, to handle any potential disconnection of the control plane from the data plane caused by failures in any of these components, the routers continue to run traditional protocols as a non-optimal fallback. This is the architecture of centralized SDN, also called CSDN. In summary, the shift to SDN1 architecture added a large number of new external dependencies, while actually we need to maintain the old undesirable dependencies on traditional protocols. This complexity is reflected in outage data. Over the past 4 years, 10% of Google's large SD-WAN outages were related to the control and the data plan, and 42% were related to the control plan alone. Overall, more than half of the root causes were in control plan or control plan infrastructures. So, the authors hope to address these large-scale outages by simplification. One might ask, why not to use a distributed protocols? It has simple infrastructure and distributed survivability. However, we cannot give up the benefits that SDN brings us. The first is the ability to run operator-defined code in control plan, which enabled operator-driven innovation. And the second is the ability to run optimized TE computation on a global view of the network, which allowed us to use the network more efficiently. And the third is the simplicity of consensus-free path selection, with only one authoritative controller deciding all paths. So, the author's goals is to achieve the benefits of both decentralization and SDN. Fortunately, the development of routers gives us opportunity. First, over the past few years, all the major router vendors have begun to support running third-party containerized code directly on the box. As a result, this enables operators to run custom control code on the router CPU. Second, a new generation of standard control and configuration APIs have matured, allowing control code to be consistent across different vendors. Finally, CPU resources on routers were expanded with multi-core CPUs dedicated to the control plan. Taken together, it is feasible for operators to run control application directly on the router. Based on the above background, the author proposed a system that decentralized SDN control plan. In order to do this, the controller is replicated on each router to move the controller in band. Looking back at the design goals, by moving the controller to the router, there is no need to rely on out-of-the-band controller hardware and software. And then the first goal has been achieved. Besides this, the decentralized architecture has no single point of failure and has distributed survivability. This achieves the second goal. Then the controller runs in a container on the router, and the control code can be customized. This achieves the third goal. Moreover, every router runs a SDN controller that first floats its local state and learns the global view, then locally computes all paths using an operator-specified traffic engineering algorithm. Since the SDN controller can compute paths based on a global view, it can fully utilize the network, thus achieving the goal of network efficiency. And finally, the SDN controller locally originates paths as source routes. Source routing can directly decide the routing path of packets, without requiring other routers to reach a consensus on the routing path. So it is a consensus-free. So the last goal can be also achieved. Let's work through with a concrete example. First, each router reads and flows its local topology and demand information. Here, the SDN uses node state update message, which includes node ID, prefix of the node, the network it is connected to, link capacity, and so on. After each router flows its node state update message, all routers in the network can build a global view of the network. Next, each node runs a global TE algorithm to compute all passes. The SDN uses an approximate max-mini fairness allocation algorithm. It is worth noting that the TE algorithm is customized by network operator and can be replaced. And then each node encodes just the set of passes it originates as strict source routes, and put them into its forwarding table. In this topology, router R0 will generate a source route to the network 1.1.1.0, which is the link ADG. Finally, when a packet needs to be forwarded on the data plane, the ingress router will determine the source routing path, write it into the packet header, and then forward it according to this source route. For example, when a packet arrives at router R0, its destination address is 1.1.1.7. That is, the network prefix is 1.1.1.0. And then, router R0 will find the source route of 1.1.1.0 in the data plane. In this case, the source route is ADG, and then router R0 will put the route label ADG into the packet header. The packet then follows the route in the header, as each router along the way pops the outer router label and forwards the packets on the link based on the next outer label. In this example, R0 will pop the label of link A and forward the packet along the link A. And then the next node will pop the label D. After passing through link D to the next node will continue to pop up label G and forward the packet along link G. Finally, the data packet reaches the egress router R1, which then forwards it to the destination host. Strict source routing enables the ingress router to decide the path authoritatively. Other transit router then follows the path, no matter what its own view of network state is. Thus, no consensus is required across transit router to decide a path. In this way, CSDN and DSDN are similar. In both, each path has a single authoritative path decision maker. Just in CSDN, it is the central controller decides the path, while in DSDN, it is the controller on the ingress router decides the path. Taken together, DSDN cuts out a large fraction of control infrastructure. More concretely, DSDN moved removed central controller jobs, regional controller jobs, dedicated server hardware, control plane network, and instrument services. And furthermore, with distributed servability, it is no longer necessary to continue run traditional protocols as a fallback. In addition, the control plane back onto the router, so DSDN added on-router containers to run the control program. This much simpler infrastructure provides a smaller surface area for bugs and greatly decreases the number of components on the critical path for routing. To evaluate DSDN, the authors built a production-grade implementation of DSDN. DSDN includes DSDN solver and DSDN controller, which are implemented as containers. The DSDN solver runs the TE algorithm, and the controller is responsible for collecting node state update messages and then installing forwarding tables. The system prototype is deployed on real router. The authors evaluated DSDN using production topology B4. B4 is a provide WAN that connects Google's data centers around the world. It uses a centralized SDN architecture. Experimental data comes from production failure events, and the evaluation included two aspects: the time required for the control plane to converge, and the scalability. Before we get into the evaluation, let me provide some background about the convergency. Convergency can be divided into three components: propagation, computation, and programming. First, during propagation, the controller finds out updated network state. For CSDN, this happens out of band going through control infrastructure, and for DSDN, this happens in band through flooding. Next, during computation, the controllers computes new passes. For CSDN, this happens at the central controller, and for DSDN, this happens on the DSDN controller running on each router. Finally, during programming, the control plane installs the updated path into the data plane. In CSDN, this is organized by the central controller and is actually quite complicated, require two-phase process that first installing forwarding entries and then tell the ingress router to enable these new passes. In DSDN, this happens entirely locally, with each router programming only the source routes that originate at that router. So, for evaluating convergency time, the author measured each of these components. In terms of propagation time, DSDN is 20 times slower than CSDN on average. As for the computation time of DSDN is 35% higher than that of CSDN on average. This is because CSDN controller is deployed on the data center server with more powerful computing resources, while DSDN is computed on the router with weaker computing resources. As for the programming time of DSDN is 1,000 times lower than that of CSDN on average. Taken together, the total convergency time of DSDN is 2 orders of magnitude faster than that of CSDN. DSDN's convergence time significantly outperforms CSDN. Regarding the evaluation of scalability, the authors mainly considered the computation time, because in previous evaluation, the SDN has advantage in both propagation time and programming time. Only the computation time is higher than CSDN. The evaluation uses a larger B2 topology, which has 6 times more nodes and 10 times more links than B4 topology. B2 network is a traditional protocol-based WAN. It uses RSVPTE as TE algorithm. The left figure shows the impact of the number of CPU cores on the computation time. RSVPTE is selected as the benchmark here. The results of computation time on the router show that even when there is only one CPU core, the computation time is still lower than that of RSVPTE. Besides, increasing the number of CPU cores can effectively reduce the computation time. The right figure is the results of scaling the traffic demand by a multiplier, representing the growth of demand in the network. We say that the computation time grows roughly linearly with the increasing in demand. And even if the demand doubles, the computation time is still lower than RSVPTE. So, router CPU resources can adequately support DSDN computational requirements. In conclusion, outages continue despite decades of experience and practices. This work presents DSDN as a new point in the design space that achieves the best of both worlds by decentralizing the SDN controller in a way that maintains the benefits of SDN, significantly simplifies the control plane infrastructure, improving convergency performance. That's all for my presentation. Thank you all for your attention.
Great. Yeah, thanks, Chengjing. Yeah, I think it's a very clean and reasonable presentation. I think convey all the key ideas, at least from my perspective. So I think we will move on to the discussion time. So Chengjing, you mentioned you have a couple questions about this paper. You want to start the discussion first?
Yeah. Hi, Alex. I have some questions. And the first question is about the node update messages. You mentioned that this network flooding node update messages, but I don't see the evaluation of this. What is the cost and frequency of flooding node update messages? Will it consume a lot of bandwidth?
Yeah, thanks. That's a good question. We I didn't talk about this in the evaluation, but it shows up in one of the graphs. It shows up in one of the graphs where we compare CSDN propagation time to DSDN propagation time. And there, we were very lucky. Google actually has two networks, right? And we mentioned this in the evaluation. We have a SDN-based network, B4, and we have a traditional protocol-based network, B2, and they're both global WANs. So we were actually able to just go to B2, which runs ISIS, and pull the logs from all the routers and see how long does it take from the moment that one router decides to flood an ISIS message to when all other routers have received it. And that's where we got our kind of flood time, because that's actually a production system that does flooding, so we could have real numbers. And it's incredibly, it's on the order of just a couple hundred milliseconds to flood globally, from the moment that the first router sends a message to when the last router has acknowledged receipt of the flooded message. In terms of bandwidth, the bandwidth requirements are very low. I forget if I left this in, or I might have cut it out, but I had a footnote in the paper at one point where I did kind of the back of the envelope for a 1,000 node network. Each node kind of reports demands to every other node, to all 1,000 other nodes. Each node also reports on its link statuses. And it was like a few kilobytes of data in these updates, and they're sent out periodically every couple of seconds. The bandwidth requirements were minuscule, so that actually wasn't a concern for us.
Oh, have you evaluated the flooding cost on a more larger topology beyond the B2 or B4 topology?
I didn't evaluate the number. Like, I wrote up the formula for what the size of the cumulative size of kind of packets being sent by an X node topology was, and it was still, again, on the order of kilobytes or megabytes total, where our links are, 10 gig, 100 gig links. So we think that it's very much in line with kind of the existing messages being sent today in the control plane. It didn't look like it was going to be an order of magnitude larger. So beyond that, we didn't worry.
Okay, thank you. And I have more questions. And the second question is, DSDN needs to know our traffic demand before we are running the TE algorithm, right? And the traffic will be. So this means that DSDN is only suitable for stable networks because we need to know the traffic demands. And then does DSDN works in a more dynamic networks? That's my second question.
Yeah, that's a good question too. So traditional networks that flood traditional protocols like ISIS or OSPF or link state protocols, they flood topology information, but they don't flood demand information. What we're proposing with DSDN is in those node state update messages, also including demand information. So today there are applications you can run on routers that sample every X packet and construct kind of an approximate view of demand, particularly coming in from kind of external interfaces. So packets coming into the network at that node, give me the kind of per each destination, what's the rate of traffic entering the network at this node? That's the information that we include in those node state updates. So it is also suitable for dynamic networks. In fact, we have a fairly dynamic network at Google, and this was designed to work there.
Okay. And I have the last question. Does DSDN only support connection-based data transitions? Can it support non-connection data transitions? I think this point is not mentioned in the paper.
Data transition. Are you talking about like TCP versus UDP?
Yeah.
Actually, yeah, that's a good question. We're, I think, completely independent of whether or not a connection is being formed. I think UDP is also fine, because I think really this is a question about how you go about estimating your demand. The way demand estimation works today, there's a paper Google put out on bandwidth enforcer, BWE, which we collect our demand from the hosts. We ask the hosts how much they're sending, and they aggregate information from all of their connections, TCP and UDP. They can see what rate they're going to be sending at for each application. What we're proposing here is that other techniques for estimating demand involve sampling packets from the router, and that sampling happens independent of whether or not there's a connection. So I do get the point, though, that maybe UDP packets are being sent at different rates, and it's not as consistent, perhaps, if it's not connection based. So maybe the estimate is less accurate, but I don't think it would make a huge difference.
Okay. Oh, thank you so much for your explanation.
Thanks for the question.
All right. So, Chengjing, you all set for the question, right? I think we have quite a couple questions from the audience. I think Rulan was also wondering about how much time we would take to flood, but I guess you already answered that question, right, Alex? So also we have yeah, right.
It looks like Rulan's. Sorry, I think Rulan's also asking about. Oh yeah, you're right. Yeah. This is effectively boils down to how long it takes to flood. Yeah, and again, it's on the order of hundreds of milliseconds, so it's pretty quick.
Cool. So, and also, Xuan Chen is asking about like figure 13 in slide 36. So, Chengjing, can you roll back one more slide?
Mhm.
Chengjing, can you go back one more slide? 36. Oh, yeah. So, Xuan says it seems like RSVP TE convergence time remains constant, even as the number of core increases. Could you explain why this is the case?
Yeah, thanks. You're right. This is a bit of a misleading way of me marking this on the graph. That number there is what we set as our threshold for how well we want to do, because it is the RSVP convergence time for B2 in production today across all of the routers using all available cores. So that's like a production measured number. We're not restricting the actual routers on what they can use to do RSVPT, et cetera. And RSVPT convergence has to do with when all routers in the network have kind of finished establishing their tunnels. And so we didn't vary the number of cores kind of for each of those data points. You're right; it's a bit of a misleading way to do it, but in a conservative way. We basically said this is the best possible value we could have when we give all of our resources and try our hardest, and that's why we're trying to beat that.
I see. Cool. All right, so I have a few questions. Let me start with a couple of probably technical ones. So since we are using DSDN is using source routing, right? So essentially we encoded the complete path from at the beginning at the source. So that's the first question is like how do you encode such path? Like how many additional bytes you need to insert into the header? And a second question is how do you handle like failover? So you specify a path, but when you forwarded the packet to one hop, one router, and then the link is down, so what would happen? So what's the safety net?
Yeah, both great questions and stuff we ran into. Actually, that first question, though, I'll repeat the question back. The question was effectively, we're proposing to do strict source routing, but if you've read papers kind of in the past in this area, the common people have thought about doing strict source routing, but the issue has been each time you have to put the full packet, full path in the header, and people haven't been able to do that before because there's not enough space. We're helped here by two things. One is in the last few years, hardware continues advancing, and backing up for a second, you might ask, why is it the case that you are limited on space in the header? It's because of the way that the packet router forwarding plane, data plane works. When a packet comes in, there's dedicated hardware that does all of the forwarding that we know that the routers do. And what it does is it chops off the first X bytes and processes that through the dedicated hardware and sets aside the rest as the payload. And so once the header is done being processed, it kind of reattaches to the payload and sends that out an interface. But the length of that X bytes that make up the header is kind of a fixed number. And so if you put too many headers in on the packet, it pushes some important information out past the point that the hardware can read. So that's where the limit kind of comes from how much data you can put in the header. So two things have happened. One is that over the past few years, packets that X has grown bigger, and so now there's enough space for 12 MPLS labels in the latest iteration of hardware that is now being sold and bought and installed. But that actually wasn't entirely enough for us. So we also in the paper introduced a novel mechanism for encoding multiple hops in a single label. And sadly, that one in the appendix, but I think it's a really cool idea. The idea is that you can kind of break down a label into two halves, a front half and a back half. And you can use that to specify one link and then another link. And then each router, it knows who its neighbors are and what the links are. And so it can pre-generate all the possible combinations of labels it could see, because it knows it could only ever see kind of valid pairs of labels. And we do the math and show that this actually this fits within the bits available in the header. And we filed a patent for it. And I think it's a cool idea. We're exploring, deploying this to expand that label size.
Cool. Yeah, I think that's a really clever. I didn't read the appendix, but it's a really clever idea. Yeah.
Yeah. Your second question. Remind me again briefly. Sorry.
The failover.
Yes, failover. So for failover, if we Chengjing, if we go back to the animation of the walkthrough, I can explain what happens there.
Okay,
Yeah, go back to the slide where there's a topology. I think that's
let's
Yeah.
see. Maybe in this.
Yeah, right here. Yeah, if you just stop here.
Okay.
And I guess if you were to go back one more slide so that the packet is at node, the pink node. Yeah, right there.
yeah.
So what happens here is a packet shows up and it has label G, and it's supposed to take that link there. All routers also pre-compute backup paths. So this is equivalent to FRR, fast reroute backup protection.
I see.
And what that says is that if the label G isn't available, so what actually happens when a link goes down? The router is notified and it invalidates the entry in the forwarding table.
Right.
And so there's often there's different priority forwarding tables, and I just explained this for everyone, for people who might not be familiar. There's different priority forwarding tables, and so we have a lower priority forwarding table that says for all link labels, what is a path around that downed link. So if G isn't available, then we pop G and put on EF, and then the packet goes EF and continues onwards just around. So that's how we protect link failures.
I see. Yeah. So essentially you proactively computing backup passes, but and you install on the data plane, so you can do this very fast data forwarding rule switching. When
Exactly.
Once the primary pass is hop is done, you can switch to the backup. I see.
Yeah, and I'll just point out that this isn't unique to like us. Traditional protocols like RSVP do this as well. So RSVP establishes a tunnel, but if any of the individual links go down, it also, at the time of establishing the tunnel, sets up protected backup paths around each link in case any link goes down. So we take the same idea, we just apply it to strict source routing.
I see. And when you compute these backup passes, you also take demand or bandwidth into the consideration, right? So you won't want to like congest a backup link, right?
Exactly. Actually, this is what we also have this in the appendix. It was its own whole body of work that we had an intern come join us and do. By having the controllers on the router, we can move those backup paths as utilization of links changes. And traditionally, you haven't been able to do that. Your backup paths are fixed at the time the tunnel is established. And so we actually have this problem where occasionally a link will go down, and at the time it goes down, the backup path is already highly utilized, and so those packets start to get dropped. So by having a controller locally, you can prevent that by moving around those backup paths.
I see. So are you familiar with the paper R3? This I think it's called resilient. I forgot. Resilient routing or resilient traffic engineering. I think it's published like in SIGCOMM 05 or I think it's 05.
I think I have read this.
Yeah. I think I forgot. I used to work with him, so I read the paper before. But I think the general idea is like it's a TE paper. It's a TE paper. So the general idea is it pre-computes some proactive paths and allocation schemes, and then it offloads it to the router. But it's like back like over almost 20 years ago. So so they use like software router. So once they sense the load or the link failures, and they can do this quick online scaling to scale the pre-computed protection plan to fit into the actual needs. I don't know if there's any connection, but I think maybe some ideas that there may be some overlapping or like a synergy between these two ideas. I think.
Yeah, I just pulled it up actually, and I don't think I've actually read this, so I'll check it out. It looks very relevant at a glance. Thanks for the pointer.
Yeah. I guess I did read a lot of old papers. Yeah. Okay, so I have a couple questions, but I will say with audience take the priority. So Eric said one thing he really liked about it, but that didn't see in the paper is that it makes a trade-off in CPU speed versus latency that will only continue to improve. And in other words, the round trip time for CSDN is basically will be bottleneck, but the speed of light, and in contrast, CPU speeds will continue to improve for the foreseeable future, thus advancing the SDN.
Yeah, that's totally true. In fact, I would say part of the reason and you're right, actually, we should have put a more explicit line about this. This is a realization we came to, but didn't, I should have called that out explicitly. But part of our goal for publishing this paper was to say, I actually want to back up for a second. The routers, these routers cost many dollars, six figures per router. And the CPUs available dedicated to the control plane are super minimal. And I think that's because they haven't needed this kind of compute before. And it would not be that, it would not be economically infeasible for the vendors to provide more compute. And part of the point of this paper was to show this is what you can do with compute even today, and this is why we need even more compute on the routers, specifically to further this advantage already. So I agree with you. I wish I had put a more explicit line about this in the paper.
Cool. Yeah, I think that that makes sense, right? So we have, as I think as mentioned in the paper, SDN people has been focusing about like a logically centralized this controller and the interaction between control plane and the data plane. And I think, well, yeah, basically, but the more I think, like the paper states, like the more components you add into a system, a giant system, the more chance you will have failure somewhere, right? So and some are even latent, as you mentioned, as it mentioned in the motivation section, right? It doesn't know that, and only after you add a new feature or update a new part, and then the bugs, different parts just emerges. So why don't we just strip all the unnecessary, I shouldn't say unnecessary, but all the features, fancy features that we added before, but or we not completely eliminated, but we offloaded to the routers, right? It's just I suggest in the paper. I think that really makes sense. Yeah, and I think also, and since Google is a major consumer of all those high-end routers, and that probably would motivate like Cisco or Arista make routers with a higher end of CPUs, I guess.
Yeah, hopefully.
Yeah, right. So I guess I have two questions, or both high levels. The first one is more related to my research area, because during our chat in Sydney, I mentioned that I'm mostly working on applying formal methods in networking, right?
Yeah.
So I guess what's your take on that? Like, does Google use formal methods to verify their networks as well, or they think yeah, we probably don't need that? If you cannot answer, if you are not allowed to answer this question, then it's totally fine.
Yeah. Yeah, no worries. I can at a very high level. This is a good question. I have to say, I'm also in the formal verification space for some projects at Google, and it's been very interesting observing in the research community how we publish these verification papers that we promise can do all these great things, but they seem to have kind of limited. They seem to be adopted to different degrees at different companies, but I see different issues kind of come up. One of the ones that I'm seeing come up now is like if you there are different just places to start kind of applying this kind of formal verification. For doing control plane formal verification, the tools that exist today, like Batfish, for example, they struggle to even kind of parse production scale configs. Like there's so many different features in there. Let alone the models in Batfish, for example, being accurate enough to capture all of the details that are being configured. Like, yes, it works for the 10, 20 node ISIS and BGP only case, but does it work for a many hundred node network with dozens of features enabled? And so I do wonder, trying to get those systems to kind of work at scale is a tricky problem. I'm really excited by all the work coming out. I see a lot of work on the techniques for scaling, like the formal portion. I think there's some work that lets you compress the topology from 1,000 nodes to 400 nodes by taking advantage of or something that you prove on the smaller topology applies to larger topology. Those technical bits are nice, but how to get these tools to be actually practically usable is a hard question that I think we're working on.
Yeah, I agree. So I guess that's essentially that's my view, right? I'm a networking person, but I only recently start to use a formal method, right? So I think the one big challenge for formal methods is how do you want to build a model that's as close as to the reality.
Yes.
And sometimes it's not like verifying the model is hard. It's like building the real model or building an authentic model. That's a really challenging part. And I think, but from my personal knowledge, I work with a couple of other companies. So based on my understanding, a fairly large amount of engineering efforts is put to just build the model to make sure
Yes.
that they
Yes.
can model. I think they start on top of Badfish, and then they try to develop, basically try to write
Yes.
parser or converter to parse their own configurations and build their models. I think. Yeah, but I think to research community, that's more a little bit like most of these efforts are engineering efforts, but
Yes.
I don't know, but I think I also I think David Walker has a student who published a paper called NV. It's called, I think it's called some intermediate representation of network configurations. It's published like in POPO or PLDI, I forgot. But I think based on the claim of that paper, it provides a more systematic way to basically to model the configuration from different vendors. I think and the paper claimed that Badfish basically and pure engineering efforts is just too complex and too time consuming and error prone, but they tend to provide a more systematic and formal way to do that. I don't know if you have read it, but if you do have it, I think Ryan is also co-author, so
I'll check it out.
Make up. Yeah, it should make up a very interesting Christmas reading.
Yeah, thanks.
Yeah, and also since we're talking about reading, I also just want to advertise a little bit about what we have been doing is we work on verification. Our group work on verification, but we are also interested in like what happens after verification. So verification essentially gives you what there is an error, there is a mistake, but it doesn't know where, it does not point to you where is this mistake and how to fix that. So essentially we figure out, we design a way and build up a plugin on Badfish. So the basic idea is like Badfish is just basically you simulate the configurations, simulate the network, and you got the data plane, and then you verify that. But if there's something wrong with the data plane, and we resimulate the original configurations, but this time we also do symbolic execution. But instead of exploring all the possible configuration spaces, we do it in a selective way, so that we can try to maneuver try to explore different variations of the original configurations, and eventually we can find a variation that gives you the correct data plane, and then by comparing the diff, we will be able to to locate the error and compute the patches. I think the basic idea is really interesting. We have a short paper at APNet last year, and we also put it on a longer version on archive. But I have to admit that the writing needs more improvement. I'll send you the link later. If you are interested, we can talk more about that. Yeah. Right. So
thanks.
we will have a few minutes left. So I want to ask the same question I have been asking for all the guest of honors in the past few meetings. So what is the biggest challenges you encounter during this work? And what's your lessons or suggestions for researchers who want to work in related areas about this paper?
Yeah. Oh, those are both fantastic questions. I think the first one, the biggest challenge, I have gathered, and from my experience so far, that there are a few different kinds of papers. And the odd thing about this paper was our proposal was not necessarily like a clever mathematical trick or something, or a thing that's like immediately very easily evaluatable. We were proposing simplification, and it was hard to build this motivation in a way that was convincing to I think reviewers, or even convincing of like, hey, this is an idea that stands kind of. I think it has landed well in this iteration of the paper, but it took a few iterations of twisting and turning the narrative to get this story to kind of come out. The problem of, hey, outages still keep happening was a clear one to begin with, but how you go about evaluating simplification was really tricky. And I think this is potentially still a weakness of the paper. Is one thing we say is we are presenting a method to simplify your network to decrease outages, but we have no way of evaluating have we decreased outages. Instead, we go over here and we evaluate how is the performance. Is the performance similar enough? And have I convinced you that this is sufficiently simpler? And do you believe me that simplification will be tied to decreasing outages? So I think this is a big difficulty with this work, is making the kind of the whole story coherent, a motivation that works with the kind of evaluation that we know how to write. Yeah, in terms of what work there is to do here, if you want to do adjacent work, luckily we have now presented a way to get controllers to run on the routers that are still doing the kind of SDN-based centralized view that is running on the routers. I think this opens up a whole bunch of possibilities, a whole bunch of new kinds of applications that can run on the routers. And really, I would think about SDN as DSDN as a platform for additional control applications, and ask what's the benefit of moving other things, kind of other control loops onto the router. Some of this stuff exists already. Like there are tools like Meta. I think they have a thing that they run on their routers that does like probing, but it's not part of their controller. It's just kind of a separate tool that they built that runs on the router. So thinking about what things like that you can do by leveraging DSDN as a platform would be a good step for adjacent research. Another thing you'll notice is that we don't do any innovation on the traffic engineering algorithm here. We just take whatever algorithm we run today. I think that there's a big space for thinking about what kind of algorithms would work well in this setting, maybe ones that decrease the amount of information that's needed, potentially. Other are algorithms that work particularly well in low compute settings. Even though we present, say, hey, there's enough compute, it's still slower on the router than it is in the cloud. And so you could even shorten the convergence time even more by coming up with an algorithm that runs faster in low compute environments. That's not something that's been needed before, because in the cloud, you've always had infinite compute. So yeah, if anyone is interested in working on any of these kinds of problems, or please feel free to reach out.
Yeah, I think that your second suggestion actually reminds me. There has been a lot of work in more like a network analytic area, like in InfoComm or Sigmetrics. What they do is essentially they formulate a problem into an optimization problem, right? And then they try to design all kinds of clever algorithms to do that.
Yeah.
But I think that I could be wrong, but I also worked in that area before, but I could be wrong. But I think most of the paper essentially is how to decompose a complex and time-consuming problem into multiple smaller problems, which you can compute distributedly and parallelly, right? So I think that actually would fit into the paradigm or the architecture of DSDN. Essentially, if you have a very complex TE problem or related problem, and then you try to, after clever decomposition, like primordial decomposition, and then you can essentially offload all the a very small scale problem onto different routers, and then you have a very happy result, right? So I think that actually opens to me. I think that opens the door to lots of potential optimization problems, because one big key difference between InfoComm and SIGCOMM community is that InfoComm tend to focus more on analysis. So quite a few papers essentially InfoComm community think is very good, but our SIGCOMM community looks at those papers and think, hey, the paper there's no application, or there's no scenario that you can apply those solutions, right? So, but with this DSDN as a new paradigm, I think those papers has a very good use case, or at least motivating cases to argue about. I think that could essentially would opens a lot of door and a new problem. How to essentially move those things, build those things into real system. I think that's good. To me, I think that could be a direction to look into. Yeah. Okay, cool. I think we are already 1 minute late from on my clock here. So since we're already finished or use up all our time, so let's thank Chengjing and Alex again for the presentation and all the Q&A and the discussion. I personally learned a lot, and I really enjoyed the conversation and the presentation. I hope all the audience too. And so just to advertise a little bit, we will meet 2 weeks later, just before Christmas, and 1 week before Christmas. And all our meetings, we have video records basically to keep archive, and we already have previous meetings video archive on website in China. But we'll also upload all the videos to YouTube, and we'll share the links with the community later on Slack. All right. Okay. So Alex, you have more any more to add? Anything to add or conclude?
No. Thanks everyone for all the questions, and Chengjing, thanks for the great presentation. It's really good. Thank you.
Okay, cool. All right. Thank you so much again,
Thank you,
Alex and
Alex.
Chengjing, and yeah, and thanks all the audience to stay late or stay till lunch. So I will see you in 2 weeks. Thank you. Thank you so much. Bye.
Bye.
Bye.